Welcome back again with Articosa. Continuing with randomized block design. I appreciate the time that I have with you to solve this question. So let's see how far we can go together. A first-year student from the University of Limpopo doing BSc in Mathematical Science has excellent performance results for both first and second semester grades in mathematics, statistics, applied mathematics, and computer science. Consider the table below displaying the results. So we have a table displaying the semester grades and modules, where semester grades are treatment and modules are blocks. So here we have first semester and second semester, which are 2 treatments, and we have 4 modules, which are mathematics, statistics, applied mathematics, and computer science, which will be our blocks. So in other words, our rows, our treatments, and our columns, our blocks. So the first question is, draw the residual plot for the performance result. So here we'll have to draw the residual plot, which is the plot of the errors versus the response, which are our marks. So our observations per treatment per block. So our response or our observations will act as our y values, and our x values will be our errors, so which we have to estimate them by the response minus the mean per treatment minus the mean per block plus the grand mean. So we'll need to calculate the mean per treatment, the mean per block, and the grand mean, so we can estimate our errors. So since we're having 8 observations here, it means we're going to have 8 errors. Beginning with our calculations, y bar 1 dot. The mean of the first treatment is given by the average of the observations on the first row, which is given by 87 plus 89 plus 92 plus 85 divided by 4, equivalent to 88.25. And the mean for the second treatment is y bar 2 dot, which is also given by the average of observations from the second row. So it's about saying 72 plus 84 plus 94 plus 89 all divided by 4, and you'll get 84,75. Now, what about the means per block? The mean for the first block is given by the average of the first column, and for the second block, the average of the second column. For the third block, the average of the third column, and for the fourth block, the average of the fourth column. So our means will be given by y bar dot 1, which is 87 plus 72 divided by 2, equivalent to 79.5. Y bar dot 2, which is 89 plus 84 divided by 2, equivalent to 86.5. Y bar dot 3, given by 92 plus 94 divided by 2, which is equivalent to 93. And y bar dot 4, which is given by 85 plus 89 divided by 2, equivalent to. So our grand mean is just the average of the treatment means or the average of the block means, which is just 88.25 plus 84.75 divided by 2, and I'll get my answer as 86.5. Now, I can estimate my errors as follows: E11, E12, E13, E14, E21, E22, E23, E24. For E11 is given by Y11 minus the mean of the first treatment minus the mean of the first block plus the grand mean, which is 87 minus 88.25 minus 79.5 plus 86.5, I get 5.75. In case you are not lost, this 87 is this value here, Y11. Your response on the first column, first row. For E12, we have your response in the first row, second column, minus the mean of the first treatment minus the mean of the second block plus the grand mean, which is 89 minus 88.25 minus 86.5 plus 86.5, and I get 0.75. E13 is given by the response on the first row, third column, minus mean of the first treatment minus mean of the third block plus the grand mean, which is 92 minus 88.25 minus 93 plus 86.5, and I get negative 2.75. E14 is given by the response on the first row, fourth column, minus the mean of the first treatment minus the mean of the fourth block plus the grand mean, which is 85 minus 88.25 minus 87 plus 86.5, and I get negative 3.75. Note that these first four errors are corresponding with the response on the first row. Continuing further, E21 is given by the response on the second row, column 1, minus the mean of treatment 2 minus the mean of block 1 plus the grand mean, which is 72 minus 84.75 minus 79.5 plus 86.5, and I get negative 5.75. E22, the response for the second row, second column, minus the mean for the second treatment minus the mean for the second block plus the grand mean, which is 84, as you can see here, minus 84.75 minus 86.5 plus 86.5, which is negative 0.75. For E23 is given by the response on the second row, third column, minus the mean of the second treatment minus the mean of the third block plus the grand mean, which is 94 minus 84.75 minus 93 plus 86.5, and I get 2.75. Finally, E24 is given by the response of the second row, fourth column, minus the mean of the second treatment minus the mean of the fourth block plus the grand mean, which is 89 minus 84.75 minus 87 plus 86.5, which is equals to 3.75. So these last 4 errors goes with our responses on the second row. So calculating the errors can be tiring, but it's a simple thing. It's all about substituting. So as you can see, we need the mean per each treatment, the mean per each block, and the grand mean to just find the errors. So they depend on the number of observations which you are having. And also, if you can look carefully at the errors from E11 to E24, if you can sum up the errors, they're going to give you 0. So this equation satisfies the model assumption about the error, that the mean of the errors is 0. Since the double summation of the errors is 0, it means that this model is appropriate for the given data. We're about to test its accuracy. So now that we have the errors, we can go and plot our residual plot versus the response. On our plot, the errors goes with the values of the response. So E11 goes with Y11, E12 Y12, E13 Y13, E14 Y14, E21 Y21, E22 Y22, E23 Y23, and E24 Y24, where our errors are going to act as independent variables, because these errors are independent or uncorrelated. So our response is the dependent variable. So under our plot, we are going to plot our response on the y-axis and our errors on the x-axis as follows. This is the plot which I'm talking about. If you can check, if you recall, under our errors, our highest value was 5.75 and our lowest value was negative 5.75. So as you can see, I even indicated what are these coordinates as I illustrated before. So it's all about where your errors and your response meet. So you just have to create a suitable interval that will cover all the errors and will cover the responses. Then you join them, you'll have this plot, which is our residual plot. And that's all. Finally, we managed to answer the first question. So you saw how did I plot. You first find the errors, which means you are going to use the formula I provided you. Then you are going to plot your errors as independent variable and your response as the dependent. Then you join your response and your errors with the meet. Then you indicate your errors and your responses, and that will be your plot. You can draw through a line joining the points. So proceeding further, the second question, use Duncan multiple range test to construct the 95 confidence interval in order to test for the significance of the semester grade means. Firstly, the Duncan range multiple test is given by this confidence interval, where RP is given by R alpha, P with the degrees of freedom of the error, then the standard error, where the standard error in this case it will be the square root of MSE over the number of blocks. Remember last time when we were dealing with treatments only, you had this as the square root of MSE over R. So now we take the R as our block, since we don't have our replication, we only have treatments and blocks here. So since we're having only two treatment mean, which is 88.25 and 84.75, we'll only have one pair. We will have to subtract the bigger mean by the smaller mean. As you remember, Duncan, we have to arrange means in order from the smallest to the biggest. Then we'll subtract the smallest from the biggest. So we'll subtract y bar 1 dot from y bar 2 dot. Then we say plus or minus r of 2. Since we compare with RP, our P here it's only 2. It was only one pair. So in this case, this R, capital letter R of 2 is just R of 0.05 with 2 comma the degrees of freedom of the error, which is given by T minus 1 multiplied by B minus 1, since we are dealing with blocks and treatments, multiplied by the standard error, which is the square root of your MSE. In this case, it's SSE, all divided by the product of B minus 1 and T minus 1, all divided by B. So this is the formula that we're going to apply. So our SSE, we find it by, is given by the sum of square of the error. So we are, this is double summation, as you can see. The sum from I equals to 1 to 2 and j equals to 1 to 4. This is the number of treatment and number of blocks. Then the error square, the sum of error square. Remember, on the last question, we calculated the errors. So we can use those errors to estimate SSE. So this is what I'm talking about. You can see E11 square plus E12 square plus E13 square plus E14 square plus E21 square plus E22 square plus E23 square plus E24 square, which is a matter of substituting the values of the errors. Then you square them, you sum all of them up. Then your SSE is given by 110.5. So we'll firstly check the Duncan table. So for our R from the Duncan is of 5% with the degrees of freedom 2 and 3, because the degrees of freedom for the error is given by 2 minus 1 times 4 minus 1, since there are 2 treatments and 4 blocks. So if I check for the value in here, as you can see, this is my value 4.501. So my confidence interval will be 88.25 minus 84.75 plus or minus 4.501 multiplied by the square root of 110.5. Remember, it's our SSE, and this part we already said it is 3. So that's why I said all divided by 3 times 4, where 4 represents the blocks, as you can see here, so that I can estimate my confidence interval from here. So the confidence interval of the differences among the treatment mean is between negative 10.1584 and 17.1584. So which means that the means are the same, since 0 is included. There is a possibility that the mean might be the same. So with this confidence interval, it will allow us to conclude on the significance of the treatment means at 5% level of significance. So remember, the null hypothesis is tau 1 equals to tau 2 all equals to 0. The effect of the treatment all equals to 0, meaning that the semester grades means are the same. And the alternative is So since there are only two, we are allowed to write this, that tau 1 is not equals to tau 2 and is not equals to 0. So at least one of the tau i's is not equals to 0. So since the summation of tau i's has to be 0, if one of these is not equals to 0, it means both of them are not equals to 0, because when you sum them must get 0. So the semester grade mean are significant, meaning that the means are different. But since in our confidence interval 0 is included, we are going to fail to reject HO and conclude that the semester grades means are the same at 5% level of significance. We concluded on the hypothesis testing to check if the treatment means are the same or they are differ based on the interval. So that's also possible. Finally, we now get to answer the last question. Assume model 2 is appropriate. Construct the Anova and draw conclusions. First thing first, we already have SSE. The only thing which are left to calculate is Sst and Ss block, and we can do them as follows. So since we know the mean per each treatment and the grand mean, it will be easy to use this formula. So we substitute, which is given by 4 into 88.25 square plus 84.75 square, then minus 4 times 2, I get my answer as 24.5. And SS block is given by, so this is also the easiest formula through using the means. It's not a long try. As you can see, 2 into 79.5 square plus 86.5 square plus 93 square plus 87 square minus 4 times 2 times 86.5 square. Then I'll get my SSB as 183. So let me construct the Anova. So I'll need SSTO now, since I know SSE already, which is 110.5 on the previous question. The total sum of square, remember, I just add SSE plus SSB plus SST. I'm getting 318. So the following is the summary table for Anova. So hopefully I did explain Anova well on the last video. So this is what we are having here, as you can see. So your MST will be 24.5 since the degrees of freedom is 1. MS block is 61. MSE is 36.83. Finally, our F values are 0.665 for treatment, 1.656 for blocks. And the corresponding F statistics value are from the F table. We're looking for F of 1 and 3 for 5%. So you check it carefully, I think it's here, 10.128. And we look at F of 3 and 3, which is 9.277. If you check carefully, our F-cal is less than our F tabulated. It means indeed we did well by failing to reject, because it supports this. So now the difference is we're testing using model 2. So now is the random effect model, the variances. So we're testing if the variance of the treatment is 0 or not. Even the variance of the block is 0 or not. So we are going to conclude based on the F cal and F tabulated for each. So looking at these values, we can see that the variance of the treatment will be 0 and the variance of the blocks will be 0.